I'm very happy to welcome today Cecilia Peralta Ferriz. She is a seagoing oceanography researcher at the Polar Science Center, which is part of the Applied Physics Laboratory at the University of Washington here in Seattle. Her research primarily focuses on the large-scale physics of the Arctic Ocean, which is what she's going to be talking to us about today. She uses satellite and in-situ observations to investigate changes in ocean properties, drivers of the flow into and out of the Arctic, as well as circulation patterns within the Arctic. Cecilia was born and raised in Mexico City, and in 2004 she earned a Bachelor's of Science degree in oceanography at the Universidad Autónoma de Baja California in Mexico, and then she did her master's and PhD in physical oceanography at the University of Washington. She's a 2017-2018 U.S.-Norway Fulbright Scholar, a member of NASA's GRACE and GRACE follow-on science teams, as well as a member of the joint ESA-NASA Next Generation Gravity Mission Expert Group. And I can say on a personal note that aside from her Arctic research, Cecilia is a wonderful person and a great friend. So with that, I will let her take it away.
Thank you, Alison, and thank you everybody for joining me here today. And I wanted to start with you by showing you these couple of pictures. Obviously, due to the pandemic, there has been plenty of challenges in our lives. And I'm grateful to say that science-wise, at least these two platforms, the Vessel Norseman 2 and the GRACE and GRACE follow-on science missions, have been a priority and very, very good and to continue our work here. And so I just wanted to acknowledge the crew members and science teams that are running this business here. What I wanted to talk to you today is about some changes in the observed Bering Strait flow and implications for the Arctic. And what I believe is the most striking result is that the Pacific winter water is no longer ventilating the Arctic's cold halocline. And I also wanted to touch a little bit into the far field forcing, which is mostly what's driving the flow variability and the trends. So Bering Strait is the only Pacific Arctic oceanic gateway. It's about 85 kilometers wide, 50 meters deep. And this picture here shows the main pathways from the Pacific entering to the Arctic, Chukchi Sea. And the red one shows the Alaska coastal current. It's fresh and warm, present summer to late fall. And the green one is the Bering Sea water, and it has two sources. One is from the west, which is the nutrient-rich anodid water, and it splits on the right, which is the low nutrient Bering shelf water. But these green waters are like the bulk of the water coming into the strait. We also have on the west purple Siberian coastal current, and this is fresh and cold. Sometimes it reaches the Bering Strait, but sometimes it does not. But the Pacific waters are very important for the Arctic. It provides a big source of heat to melt ice. And for instance, in the spring, it onsets the sea ice melt in the Western Arctic. And year-round, it is the subsurface heat for about half of the Arctic Ocean. It's also important because it's a significant contributor to the Arctic fresh water. It's about a third of the whole budget, and the other two being PE minus E and the river runoff. It also, the Pacific water is important because for ecosystems, because the Pacific water provides the most nutrient-rich water entering the Arctic. And it's also important for Arctic stratification. In winter, the Pacific waters tend to form a cold halocline layer, which is what insulates the sea ice from the underlying warm Atlantic water. And it's also impacting global climate. And there's some studies that suggest that it's modeling studies that doubling the flow of the Bering Strait affects the AMOC and the Gulf Stream. So let's dig a little bit into this Bering Strait. The picture of the right shows the location, the color-coded balls are the location of the moorings that at the University of Washington have maintained since 1990. Now, not all of them have been maintained. The Bering Strait is divided by the Diomede Islands over here. And the Western Channel, the A1 mooring, is in Russian water. So, of course, that has been representing a challenge into measuring over there. But we have measured continuously in A3 what we call a climate site. And we have shown that this climate site represents a good average of the Western Channel and the Eastern Channel. And if we add the contribution of the Alaskan coastal current with A4, then we are good at representing the entire bulk of the Pacific flow. And so this flow is what I'm going to show on the pictures on the left. So what we are looking here at is the transport on the top, the temperature, and the salinity in the bottom. And I want you to focus on the black lines, which is what our climate site is giving us, the total transport. And these trends are increasing. The transport is increasing, the temperature is warming significantly, and the salinity is also freshening. And this is the only Arctic gateway that is showing significant trends. The heat and freshwater fluxes are also increasing. And here I'm showing in black again the climate site A3. And on the top is the heat flux, and the bottom is the freshwater. And the red is with the added contribution of the Alaskan coastal current and the surface layer and the heat and stratification here in this case, the freshwater. So let's dig a little bit more into this warming, and we are going to do that by looking at warming, cooling, and ice-free days. The figure on the top shows the first day above 0 degrees that we find in the Bering Strait. And this is given by the black line over here, and the vertical axis is the Julian days, so the days of the year against the years. And what we see is that the first day above 0 degrees, that it's warming earlier. And these are just the lines that represent where in the months we are, like about 150 days is 1st of June, up here is 1st of July. And before we were having this first above 0 degrees Celsius around mid-June, and now we are well into May. About cooling, we are also sending the last day above 0 degrees Celsius a little farther in time. So before we were seeing it in mid-November, and now it's well into mid-December. And so consequently, we are increasing the amount of days that we have warm water in the strait. And before we have, say, between 5 and 6 months, and now we are well above 6 months. At the rates that we are seeing here, it's about we're having longer warm water by 2 days per year or so. And there's strong implications for the Arctic with this warming. As I mentioned before, the Pacific water the heat triggers the sea ice retreat. And this is shown as an example here by the figure of the sea ice concentration in June 2007. And it shows these indents that are given by the white arrows here representing the pathways of the Pacific water. So, of course, this is also allowing for more shortwave radiation to be absorbed into the open ocean. But there is only a limit to which the solar radiation can come to the Arctic, right? And this limit is just given by the sea ice extent. But there is really no limit to the warming of the Pacific water itself. So that can just keep warming, and that will continue to be a source of heat for the entire Arctic. Now let's dig a little bit into the freshening. And here I'm showing the 30-day smooth salinity. And the gray lines for each of these panels are the monthly values of all the years. And then the black lines are the climatology of all these years, and the red lines are the given year. So 2016, 2017, 2019 over here, and the farthest east is to the right is the 2019. And this one is in brown just because this is brand new data, so this still requires a little calibration. And I don't expect this to change significantly, but just wanted to include it here to show how much fresher we are also seeing these winters. So if we look at the salinity trends by month, what we see is that regardless of the period that we consider, whether we look at the period from 1990 or from 1998 up to 2015 or 2000 up to 2015, or sorry, 2018, all of them are showing a significant freshening in the winter months. And this is a little striking, like we are used to seeing salinization of about maybe 1 PSU within the winter. And this is typically associated to the cycle of forming sea ice. So we have the brine rejection that makes the water column saltier. And that is about 1 PSU in the season. But in these years, we are no longer seeing this seasonal cycle anymore. One of the implications of I'm going to talk about the implications of winter freshening now, and this is a plot of the 30-day smooth salinity from our climate site. What we used to see was maximum salinities about 33 PSU in the winter. What we see now are maximum salinities that are about 32.5 PSU, and these are in summer, not in winter anymore. And if we look at this in terms of a volumetric TS diagram, this is for 1991, and this is representative to the prior years. Like it's showing for this year, but it's also representative for all of these ones, right, in the early 2000s. And what we see is like these two bulks of water masses very distinctly. The picture to the right is the volume versus the salinity plot, and red line is warmer than 0 degrees, and blue is colder than 0 degrees. So in prior years, the summer water, the Pacific summer water, was right there and fresher than winter water, which is given by Pacific winter water, PWW. Now, more recently, an example is 2018 year, but it's representative to all the 5-6 years recently. And we see that now the winter Pacific water is fresher than the Pacific summer water. Now, because the salinity drives the density in these cold waters, we can see the same picture if we look at into the perspective of the density field. So now this plot is showing the 30-day smooth sigma values, and we see that the Pacific winter water is less dense now by about 0.5 kilograms per meter cube. So we have the same picture over here. The one to the right is now volume versus the sigma values. And we find that in prior years, the summer water was less dense than winter water, as we know it. And now the winter water is the same density as the summer water, as shown over here. And now, if we can locate these waters where they go into the water column, this is a picture in the right of 2002-2003 data. It's a section of the Beaufort Slope, and the colors are temperature and the lines are salinity. So essentially, our Pacific winter water then was located somewhere here, about 100 to 150 meters deep. But now the Pacific winter water is roughly 50 to 100 meters. So it's 50 meters shallower, and it's not only that, it's at the same depth as the Pacific summer water. So we typically define the cold halocline layer, that layer that insulates the sea ice from the heat of the Atlantic water, as I said before, by this sigma density of the 26.5. So this is represented by this TS diagram over here. And here's the winter water. And if we want to be less conservative, we can even consider 26.2 kilograms per meter cube as one sigma value, defining the beginning of our cold halocline waters. And if we separate our volume transport into density ranges, here we have over time, the gray is showing the total transport. The pink is showing the waters that are lighter than 26.2. And the black lines are those that are heavier than 26.2 in density. So the black and the pink are adding up to the gray one. And here I'm also adding the green one that absolutely is a measure of the ventilating cold halocline. So these waters do ventilate the cold halocline layer, and these pink ones do not. And what we see is that before we had these waters being roughly 0.3 Sverdrups, but in the past recent years, especially since 2014, these waters are zero. Like there's no contribution whatsoever to ventilate this water. Essentially, Pacific winter water is no longer ventilating the Arctic's cold halocline. Now, let's dig a little bit into what drives the flow through Bering Strait. And the total transport is driven by a local wind-driven forcing and a far-field forcing. And we do this separation by linearly fitting hourly transport and wind data such that the total transport equals A, which is the far field, or what we typically call the pressure head term, plus B times the local northward wind. This is what we call the wind contribution of the flow. And here is the flow in its components. the brown one shows the wind contribution, the black is the total, and the green is showing the pressure head contribution. The first thing to note here is that there's really no trend in the wind forcing. It hasn't changed very much. So that the increasing trend in the transport has to be due to the pH term, the pressure head term. A couple more things to highlight is that this is a climatology values of the V velocity, the total northward velocity, for a couple of periods. In black is earlier period in the 90s, and the red one is showing later periods. What we show is, first of all, the in situ meridional velocity is largest in the summer, and also that the recent trends are largest in July, in the summer as well. And the local wind is rather a more important driver of the velocity in the winter, and this is given by the velocity correlated with the local wind. So the correlations are about 0.8 in average, so these are much, much higher during the winter months, and so November, December as well. So the wind is not being able to explain the variability in the summer, which is when we have the strongest flows and when the trend is also increasing. So we're able to turn our head to what the Gravity Recovery and Climate Experiment, or the GRACE mission, is doing. And in the ocean, so this mission measures the changes of mass on the Earth. And for the ocean, this essentially gives us the ocean bottom pressure changing over time. And what I'm showing here is two figures of correlation. The V velocity on the left, so the total velocity on the left of the strait, correlated with the monthly GRACE bottom pressure field. This is from 2002, 2006 to 2016. And when we remove the the local wind forcing, we get the picture to the right, which is the pH term. And what we see is that the East Siberian Sea has this strong signal of low pressure, and also there's an increase in flow here. It's associated with increase in ocean bottom pressure in the Bering Sea as well. And this pattern is consistent with theory of flow through channel with rotation, and relating the sea level that we find upstream from the channel and being high, as we see over here in the strait, and downstream we see a low sea level here, which is also what we observe here with GRACE. So when we look at this area, we found before that when we decompose this region of the ocean bottom pressure in empirical orthogonal functions, the leading mode has this strong drop in the Siberian Sea, and this is highly correlated, significantly correlated with the pH term, especially. It's correlated also with V velocity, but more strongly with pH term. The second mode is also significant, but it does not correlate very well with the pH term. In fact, it's not a significant correlation here. But it does show that this plays a role with the flow later on. So for the year round, about 35% of the variability in the pH term is explained by this Siberian Sea low. But if we look at the summer months only, we essentially explain about 70% of the summer flow variability. And we only have one leading mode. And we found that the dynamics associated with this mode, given by this correlation between the zonal winds and the principal component time series associated with this first mode, are such that the strong westward winds along the Siberian shelves are such that they push water to the right in sense of an Ekman surface transport, and then that reduces the mass in the Siberian Sea, increasing our flow. Now we have also data from dynamic ocean topography from ENVISAT and CryoSat, and we have this for 2003 through 2014. This is a product by Armitage 2016. And I wanted to show this because I wanted to see if DOT is giving the same behavior as ocean bottom pressure, if they are consistent with each other. And now at these depths in the East Siberian Sea, it's about 50 meters in average. So it's very shallow. So we would expect both DOT and ocean bottom pressure to behave the same. And we do see the same correlations with V velocity and pH term, so much stronger with pH term in the East Siberian Sea. And the EOFs themselves are also very similar, very consistent with each other, and the same type of level of correlations are also of the same level. So summer EOFs of DOT are consistent with summer EOFs of GRACE bottom pressure. Now the question is, is there a declining trend in East Siberian Sea bottom pressure and DOT that can be driving the pH term trend? And so to explore that, I'm looking at the 2003-2014 data, and this is a period where we also have a very strong pH term trend, increasing trend. So the top left is showing the annual mean trend of the zonal winds. Westward will be blue, eastward will be red, and sadly we see not much, right? Like what we see, this bright sign right here in the Siberian Sea if you squint, but we do not see much significance. Like the significant values are thicker lines, and non-thick are the thin ones are not significant. More disappointingly, we see ocean bottom pressure increasing. So life is not as easy, right, as I would have hoped. But if you squint, you do see that DOT has these low values trending low here in the Siberian Sea. So the picture is not clear when we look at the annual means in the trends. But if we look at the July, August, and September, which is when we have the strongest pH term increases, we have hints of this being the same driver. The summer shows that there's weekly increasing westward winds along the Siberian shelf, so at least they are in the right sign, and sometimes they are significant, like we are here, but sometimes it's really not. So this is really not yet a clear picture. Now, keep your squinting in, and then we can see that the East Siberian Sea has no trends at all, no significant trends at all. You see some blues here, which is good in the Chukchi Sea, but really nothing in the East Siberian Sea. And with DOT, you don't have to squint much. You do see many more blues, and that's great. So this is showing here, except that when we have the strongest forcing, we do not see much of a low here, a low DOT here, and we do see a strong low DOT over here. So there's indication, and this is probably enough to actually drive the trend that we observe. But the fact that bottom pressure and DOT are so distinct and not giving the same answer leads us to believe two things. Like if we do believe these trends in bottom pressure and DOT, then there has to be a steric compensation within this region. And we can see that by taking the difference between the two of them. So we get steric height as DOT minus OPP. And this is the trend of that steric height. And then following Armitage, we can assume that at these cold temperatures, the steric height is mostly, the density change is mostly due to the salinity change. The steric is halosteric. Therefore, we can get a salinity value associated with this steric height. And the trend is such that it has to increase in order to balance the opposing trends of bottom pressure and DOT. And this salinization is about 0.06 PSU per year. And some scaling analysis, I have tried to determine what could be creating this region to get saltier. And some scaling analysis suggests that the largest term that could do this, at least more easily over this time, is the increased advection of the Pacific waters into the area. So to summarize, we show that Bering Strait volume, heat, and freshwater fluxes into the Arctic are all increasing. We also saw that the significant warming of the Pacific waters is likely to contribute to more sea ice melt. And the striking result is that the dramatic winter freshening has resulted in less dense Pacific winter water, which is no longer ventilating the Arctic's cold halocline layer. We also mentioned that the increasing trend in northward Bering Strait flow is due to the pH forcing and not due to the local wind forcing. And the pH term trend is largest during the summer and potentially linked to, albeit weakly, the increasing summer westward winds along the Siberian shelves and a declining summer East Siberian Sea DOT, but not ocean bottom pressure. And if we consider these trends are accurate, then it requires an increasing trend in the East Siberian Sea in the salinity of about 0.06 PSU per year, and which we argue is due to an increased advection of Pacific waters into the region. However, we do not have in situ data of salinity in this region to corroborate that this is indeed a truth, that it's happening, this salinization is happening. And that's all I have. Thank you. happy to take questions.
Great. Thank you very much. Lots of hands clapping. So I think we have one question already from Gokhan. Do you want to go ahead and unmute yourself?
Sure. It is essentially related to sort of the first two items or the plots that you show here, time series plots. Is it possible to put these changes in historical context? In other words, can you say anything about prior to 1990?
That's a very good question. I will have to look around. Because yeah, I do not have the answer for that. I'm not really sure. I'm pretty sure because we have discussed when we go to our work in Bering Strait, we have an opportunity to talk to local communities there, and so but what we typically discuss most is the sea ice presence, how they used to have much more ice there, but I don't recall anything about the flow itself increasing. So I will have to look back, but yeah, that's a very interesting question.
Thank you.
Any other questions from the audience? Maybe while people are thinking, I have a question about, you mentioned, you don't have in situ data from the East Siberian Sea. Are there any kind of hopes of getting data or, some kind of verification for your last point here?
So I think my hope is so there's some climatology values, but I don't think those are enough for what I can see. But there's a recent paper, and I'm forgetting the author now and or colleagues, but there's a recent paper of the Laptev Sea. So what I think I can do is, and I just started reading this paper, but it's not quite the East Siberian Sea, but they do have the Laptev Sea has the largest river discharging into the area, the Lena River, and they talk about the flow, how this plume can be potentially entering the East Siberian Sea or just going up north towards the Central Arctic. My screening analysis suggests that the runoff, even if you divert all the Lena River, it shouldn't be enough. It wouldn't be enough to salinitize this much. But I think can give me hints, looking at the Laptev Sea can give me hints of how much actually this water is coming. Not necessarily just for the river, but maybe pure, if that region is fresher anyway. So that can also give me maybe a sense of what we could see or hope or expect in the East Siberian Sea. So yeah, I look into that, and hopefully I will continue to look around if there's any Russian data that I can get a hold of, because it's still unclear. So far, I can't.
Great, thanks. And I see we have another question from Isabella.
Okay, sorry, it took me a minute to get unmuted. Thanks for a really great talk. My question was about that last point as well. So you kind of started talking about it a bit already, but it sounds like, so the Pacific water is freshening, but more of it is potentially going to the ESS. Have you been thinking about like if there's some kind of feedback going on that? Yeah.
Yeah, that's tricky, because of course, if we're seeing freshening, how do we expect to salinitize the area, right?
Yeah.
However, the Pacific water is still saltier than the Siberian Sea waters, and so that source still can salinitize from our original ESS bulk salinity. But yeah, I think there's many other mechanisms. For example, the area has polynya, it's a polynya region, right? So maybe we are making more ice and salinizing in that region over time. However, again, some scaling analysis showed me that can contribute, but it's not as large as potentially the Pacific influence. Another thing that we explored was the upwelling of Atlantic water reaching all the way to the Siberian Sea. And that could do it, especially for 10 years or 12 years that we are considering here, that could do it. However, to do that, we have to have sustained westward winds to do it, and those seem to be weak. So yeah, I agree. There could be some feedback factors that are just messing around or they're not just giving us a clue for one signal to be the culprit of,
Yeah.
of this.
Thank you. It's really interesting.
Thanks.
We are at the end of the scheduled webinar time, but we have one more question. Cecilia, if you have time to stick around.
Sure.
But I want to give people a chance to thank our speaker again and leave if they need to. And then we'll take our next question from Dimitri.
Hi, Cecilia. Very nice talk. Thank you. I have a question about the impact of Pacific water on sea ice. Do you have any estimates? What kind of impact are we talking about?
What do you mean input?
Impact. So how much ice can it potentially melt? So this increase of Pacific water inflow.
Yeah, so I see those calculations. Rebecca, we work on those calculations, and I believe that in 50 meters of water, just again, this is just scale analysis. I think we can, with a half change of salinization, I mean, with a half PSU, I think we can melt you're thinking of the increasing of the flow, but warmer flow. So this heat can melt about a meter, I believe, no, half a meter for every half of PSU of water increasing.
Oh, okay, so how far in the Arctic would this impact be notable? Beyond the Chukchi Shelf? Can it impact the Beaufort Sea, for example, the Beaufort Sea?
I think it can, because this will be a subsurface. So whatever does not melt immediately in the surface and opening the water to seashore side, that water will stay underneath. And this, this has to enter in my opinion, has to enter the Beaufort Sea. I don't know if it's going to be the main source within the Beaufort Sea, but I think it's going to be it is a good source for sure.
But it will be subsurface, right, in the Beaufort Sea, the Pacific?
I think it will be subsurface, yeah. And but again, so this heat is being maintained very, very shallow. Yeah, so it is subsurface, but it does have the capability to just melt more ice. I think the heat can affect, of the Pacific can affect up to about half of the Arctic. I think that's a fair estimate to say. Whether it will all melt the ice, that's a question. But there to potentially do it, yeah.
Okay, yeah. Thank you, Cecilia.
No problem.
Okay, well, unless there are any more questions, I just want to thank Cecilia again for a really great talk, and thank you all for coming.
Thanks, Arizona. Thanks, everyone.